Welcome to this lecture on mechanical vibrations, and this is the continuation of chapter number 2. As the students of section A already know that we have covered chapter number 2 in some topics of chapter number 2 in week 6. So few of the topics were left, and I intend to cover those topics in this lecture. Whereas for Section B students that have been recently merged with Section A, the initial topic uh, of this chapter number 2 will be converted into video lectures by Mr. Shahroz Tahir, and the students of Section B can listen to those video lectures in continuation with this lecture. So we're going to speak of what sort of information we can retrieve from the roots of the characteristic equation, and we have studied how to develop the equation of motion of vibrating systems, especially the damped vibrating systems, in week number 6, and we studied the characteristic equation, and we came to know that the solution of the damped system actually depends upon the roots of the characteristic equation. So the roots can give us a lot of information about the vibrating system. So here we have as you can see, an equation of motion for damped system, and you can look at the constant coefficients here in this characteristic equation of a damped free vibrating system. The constant coefficient appearing with the s square, now this is a polynomial in s, and the constant appearing with s square is the inertia of the system. The constant that is appearing with the s term is the damping in the system, whereas k is the elasticity or stiffness property of the system. And we also know that since this is a quadratic equation, its roots can be represented in terms of the damping ratio zeta. This we have done in the previous lectures, how to represent roots in terms of the zeta. And so this equation, since it's a quadratic equation, we're going to have two roots, s1 and s2, given like this in terms of zeta. And we know that the response of this kind of equation of motion, okay, if it has two roots, can be represented like this: c1 e raised to the power s1t plus c2 e raised to the power s2t, where s1 and s2 are these roots. So this is how we represent the response of a second order homogeneous linear differential equation. Now, how can roots helps us in understanding the behavior of the system? So we have to keep in mind these points. For example, we can look at the first point: for convergence or a stable response, negative roots are must. So we must have negative roots, or we can say that the characteristic equation in our system should have negative roots for convergence or for stability. Larger negative roots means faster decay. So because if a negative number will appear as the power of the exponent, let this number be x. So if this x is large, then the decay, this exponential decay, will be faster. So for larger negative root means faster decay. And why we need negative roots for convergence? Because we know that these negative roots will decay. Okay, so this will not going to decay, it will always going to increase in time. However, this root or this function exponent with a negative function will going to decay with time. So that is why negative roots are so important in vibrating systems. And larger negative number means faster decay, so a larger number will going to decay faster. If roots only contains imaginary part, then the response will be of oscillating nature, and this we have seen when we were dealing with the response of free undamped systems, because there in that case the roots were plus minus iota omega n. Or in other words, if you say that zeta is 0, if you make zeta 0 here, then zeta will be 0 here, and you will have only imaginary root, that is plus minus iota omega n. So this real part will be 0. So if you have only imaginary part in your roots, then the response will be of oscillating nature. And indeed we showed that the response of a free free undamped system was of oscillating nature, something like this. Okay, so it was of oscillating nature, and it was marginally stable because neither it grows in time nor it decays. Also, by looking at the root, we can say that if the root has a larger imaginary part, this means higher frequency of oscillations. So low frequency of oscillation would look something like this. They it's a low frequency oscillation. Okay, but a high frequency oscillation would look like this. So the spaces between these oscillating response will be very narrow, and this means that this kind of a response has higher natural frequency, higher frequency of oscillation, whereas in this case the natural frequency or the frequency of oscillations are small. So larger imaginary part means higher frequency of oscillation. And also we can plot the roots on the real and imaginary plane, as we're going to see in the next slide, that we can plot our roots on the real and imaginary plane, and we can study all these points that I have discussed from 1 till 5 on this plane as well. Another very important aspect is that from the information of roots, we can also get the knowledge regarding the inertia, that is about the mass present in your system, the stiffness, that is about the value of K present in your system, and the damping, that is the value about of C present in your system. So by just having information about the roots, or in other words, if the values of the roots are given to you, you can actually work backward, and you can find the auxiliary equation, and you know that the auxiliary equation is a quadratic equation. Okay, so if the roots of the quadratic equations are given to you, you can work always backward, and from the knowledge of that root, you can recover the quadratic equation, and you can study that what is the value of M, what is the value of C and K in your system. Okay, so the knowledge of root is therefore valuable for us, and we can get all the set of information from the roots of the equation. Now we're going to see how we can plot these roots on the imaginary and real axis. So we have a real axis on the as x-axis, and we have an imaginary axis as the y-axis, and we can see that all the roots. Okay, so if you look at this point, this black dot represents location of the root. So this black dot actually represents this response. This black dot here represents this response, whereas this black dot appearing here represents this response, and so on in this entire figure. So there you can see that there are a lot of black dots plotted on this diagram, and each one of them represents the value of the root of your system, and thus you can have a lot of information about the response by looking at these roots. So what this graph is telling us, what this figure is telling us rather, is that if we have an imaginary and real axis, we can plot our roots, okay, according to the real part and imaginary part of the roots. We can plot the dot, and it's telling us that all roots that are plotted on the right hand side of this plane, okay, the right hand side of this plane appears to be unstable, because or marginally stable only, because you see that their amplitude is actually growing in time. No matter they are of oscillating nature or they are of non-oscillating nature, okay, but what you can see is that their amplitude is actually growing in time. Sorry. So this is growing in time, and this has also grown in time. And when the amplitude actually grows in time, it means instability. On the other hand, you can look at this figure. These two are actually marginally stable only, because they don't have any real part of the root. They only have imaginary part. The real part for these systems are zero, and when the real part is zero, they are oscillating in nature, because they have only imaginary part. So they are oscillating in nature, and they are marginally stable because the amplitude is not at least growing in time compared to all these things, all these responses. The response of these two is still not oscillating, but they have at least fixed amplitude. They are not growing in time. So this root here represents a lower value of imaginary part, because it is plotted nearer to zero, whereas this one represents a higher value of imaginary part, because it is plotted farther away from the zero of the coordinate system. And so a lower imaginary part means low frequency. So this is, you can see that the distance between these peaks is much larger compared to the distance between these peaks. So this means that this is high frequency vibration, okay, because the imaginary part of the root has higher value, whereas this one has a low frequency, because it represents a lower imaginary value. And this system here is basically represents zero roots. So it has a zero imaginary root, a zero uh, real root, which means a trivial solution, and trivial solutions are not important for us. So what we conclude looking at this figure is that uh, positive roots never decay, okay, because you see that these dots are always plotted on the right hand side of your graph. So they are plotted on the positive real axis. Actually, all these roots that I am encircling, rep, they have positive real parts, okay, they have positive real parts, and therefore they are growing in time. On the other hand, if you look at the roots plotted on the left plane, left hand side plane, these responses are always stable. These responses are always stable, okay. So if you look at this root, okay, this is much closer to a zero, but it has a negative real part because it is plotted on the other side of zero. It has a negative real part. Okay, no imaginary part, but only negative real part. So it is of decaying nature, but it will take some time before it come to rest because it's not a big value. It is much closer to zero. If you look at this root, it has a real part only, no complex part or imaginary part involved because it is plotted on the horizontal axis only here. So it has only a real part, but it is much farther away from this zero. So this means that it is going to decay faster compared to this response. So these systems which are non-oscillating, why non-oscillating? Because they don't have any imaginary part in their roots. These dots are only plotted on the horizontal axis, so they have zero imaginary part, only negative real roots. And we know that these systems, which are non-oscillating in nature, they represent either the critically damped systems or the over damped systems, in which the roots are real repeated or real distinct, but they all have negative values. Okay, and they have no imaginary parts, so they are non-oscillating. Whereas if you look at these roots, then this root especially, this root has a real part as well and an imaginary part as well, because it is now plotted at a vertical distance, so it has some imaginary part. Okay, it has this imaginary part and this real part. So a negative real part and an imaginary part. This means that this system will be oscillating in nature. So you can see that there are oscillations for all these rest of the responses plotted here on this plane. You can see, you can spot the oscillations, and these oscillations are of decaying nature. As you can see here, these oscillations are of decaying nature. They are decaying with time. Okay, so this root has a higher negative real part. Okay, so therefore it is coming to zero faster compared to this one, because this has a root which has a lower value of negative real part, and imaginary part means signifies the fact that they are oscillating in nature. Okay, so again the frequency is lower for these responses and the frequency is higher on these responses because these roots have larger imaginary parts compared to these roots plotted here. So a lot of information about the response we can get from looking at the values of the roots, and if we plot them on the imaginary real part, we can figure out that whether the system will be stable or unstable. It will be of oscillating nature or non-oscillating nature, and that is a very valuable information. So you have to keep these 4 to 5 points. Okay, what sort of information you can get from the roots just by looking at the values of the root. Another concept that is important uh, is the stability of the vibrating systems, and this is the actually the last topic of chapter number 2, stability of vibrating systems. uh, so how can we define the stability of a vibrating system? So formally a system is considered to be stable if its free vibration response approaches zero as time approaches infinity, or we can say that it must have negative roots, because negative roots satisfy this definition, this statement. If the roots will be negative, then the response will decay in time and will obviously going to reach a value of zero as time will reach infinity. So a system is considered to be stable if its free vibration response is stable and converges with time. In the second definition, you can also say that a system can be considered to be only marginally stable if the free vibration response neither decays nor grows in time. So this is free undamped vibration. Okay, this is the response of a free undamped vibration, because a free undamped vibration response neither grows in time nor it decays in time. So you can call it a marginally stable response. But if it decays to zero, completely to zero, as time increases, then it will be a stable response or a fully stable response. These definitions are also valid for force vibration response. Okay. Only linear systems for which m, c, and k do not change with time. This stability is only concerned with the linear systems. Okay, the system has to be linear. It does not has to be a non-linear system. We are not talking about non-linear systems. System has to be linear, and this means that small oscillations, and for which the values of the system parameters m, c, and k, they do not change with time. That is, we are speaking about time invariant systems. So time invariant systems are systems in which the values of constant coefficients appearing in the differential equation of motion, that is m, c, and k, they do not vary with time. Now, by looking at the equation of motion or the characteristic equation of your system, you can actually predict few things about the stability of a vibrating system. For example, if we speak of this point number one, now if any term in the characteristic equation, okay, correct, you can look at the characteristic equation, or you can also look at the equation of motion. If any term in the characteristic equation or the equation of motion is negative or comes out to be negative, this means that if the sign of the constant coefficients, that is the value of m, the value of k, or the value of c, if the sign of these three system parameters, mass, k, and c, if it comes out to be a negative number, okay, then your system will become unstable with time. So obviously we do not design unstable systems. We have to design a stable system. So when you drive the equation of motion of your system, and during the derivation of the equation of, and you know that the equations of motion of vibrating systems can be derived using Newton's second law of motion, F equals to ma, or m equals to j theta double dot. So if you have done some mistake, okay, then a negative sign can appear in your equation of motion, and this means that basically what you have done is not right, because a negative sign is indicating that your system will become unstable. So you have to keep a very good track of your derivation when you are driving the equation of motion of your system. Especially you have to look at the sign of the inertia term, the stiffness term, and the damping term. They all must be positive in your equation of motion. None of them should be negative. If anything is coming out to be negative, then this means that your system will become unstable with time. This is the first point that you should check while looking at the characteristic equation of your system or the equation of motion of your system. Secondly, if any term in the polynomial in S is missing, one of the roots will be positive and the response will not be stable. So as you all know that the characteristic equation is will be a quadratic equation, a polynomial in s square plus s plus some constant equals to 0. So if in this polynomial any term in s is missing, then your system will have a positive root, and positive root, as we see, positive root means instability. So for example, if you look this characteristic equation, this is the characteristic equation of a free undamped vibrating system. Ms square plus k equals to 0, and here you can see that this characteristic equation is missing the term on s. So this polynomial is incomplete in terms of powers of s, because s raised to the power 1 is missing. Hence it is only a marginally stable system, it is not a completely stable system. So because the s part is missing in this characteristic equation. Also, the third point is that if the linear model of the system is stable, then it is not possible to find a set of initial conditions that will make the system unstable. So as you all know that in order to vibrate a system, you need to provide some initial conditions, either in term of the velocity, or in terms of the of displacement, whatever, or maybe the combination of both. Only then the system will going to vibrate. So if your vibrating system is linear, okay, again we are talking about linear systems only. If the model that you are dealing is linear, then there is you can actually literally provide any initial condition to this linear model of your system, and you will always going to observe a stable behavior, because it is not possible to make this vibrating system unstable uh, by providing it any initial value in terms of displacement or velocity. You cannot make it unstable. It will always remain stable if its linear model is stable. But on the other hand, if the linear model of the system is unstable, okay, somehow if the linear model of the system uh, is coming out to be unstable, okay, for some reasons, then there might be certain set of initial conditions that can make the system stable again. So in this third point we were talking about that it is impossible to make a linear vibrating system unstable by providing it any kind of an initial condition. It will always remain stable. However, if the linear model of the system becomes unstable, or it is unstable, there can be certain set of initial conditions that can make it stable again. Okay. Now, for example, consider this equation of motion, and this equation of motion will going to have a characteristic equation of s square minus 1 equals to 0, because x double dot can be converted to s square. Okay, then there is no x dot appearing, so s is missing, right? And this is a constant, so 1. So s square minus 1 equals to 0. This gives us root s equals to plus minus 1s. Now you can observe that since the characteristic equation and the equation of motion, it has a negative coefficient, okay, and also there is a polynomial in s missing in the characteristic equation, okay. S, the term s raised to power 1 is missing, and also there is a negative sign appearing in this equation of motion, or the characteristic equation. There is a negative sign as well. So we can say, by virtue of point number 1, we can say that this system will be unstable. And since one term is missing in the polynomial of s, one root will be positive, okay, by the definition, or by the statement of point number 2. So this system will be unstable in time, okay. But how it will be unstable in time? You look at the response here. When you have two roots of second order linear homogeneous differential equation, you can always have the response like this. You can always have the response like written like this. And in this response, you can see that since one of the root, okay, is positive, it will going to make this exponent positive. So this means that this part of the response, C2 e raised to the power t, will not decay in time, and it will going to make your system unstable with time, maybe at some point. So this means that if we can set initial conditions in a manner that this C2 vanishes from our response, if the contribution of this C2 vanishes from our response, our entire response will become stable again, because C1 has a power of exponent that is negative, power of exponential that is negative, and negative powers of exponential will always decay in time. So this C2 is making things difficult for us. So we have to select some initial conditions, set of initial conditions that can eliminate this C2 from our response. And you can check now that if we assume that the displacement at time t equals to 0 is, let's say, 1 centimeter or 1 inch or 1 meter, and the initial velocity at time t equals to 0 is set to be negative 1 centimeter per second, inch per second, or maybe meter per second, then this C2 can become 0, because x1 can be given like this: C1 e raised to power minus t plus C2 e raised to power t, and x dot t, sorry, and this x dot here will can be written as minus C1 e raised to the power minus t plus C2 e raised to the power t. So if now we solve these two equations together simultaneously, we can find the values of C1 and C2. And what we found out in the end is that C2 comes out to be 0. So when C2 becomes 0, our response reduces to x equals to e raised to the power minus t, and this response is stable because it has a negative root only, or the power of the exponential is negative. So this solution will decay with time and thus will become stable according to the definition statement given in point 1. So we see that even if the linear model of our system comes out to be unstable, or if the requirements of point number 1 and point number 2 are not being satisfied, then still we can make that system stable by selecting some appropriate initial values. Okay, of course this will be a time consuming process. You have to find out by trial and error these initial values, and your system will then become stable, not grow in time. So what we learned in today's lecture is that by looking at the roots of the differential equation, sorry, the characteristic equation of the equation of motion, by looking at the roots, we can predict a lot of important aspects about the response of our system, and we have learned about the stability of the system as well. The first 2 points are the most important points. So whenever we are trying to check the stability of the system, we have to focus on these 2 points. Okay, there should be no negative sign in the equation of motion or the characteristic equation. Okay, and the polynomial should be complete, the polynomial in S. So these are the important points that we have to keep in our mind while we are looking at the roots of the equation of motion, and while we are dealing or trying to analyze the stability of the system. In the next lecture, I will going to solve some problems related to these topics, and some problems related to the previous topics as well that I have covered in week number 6 in section A. Until then, you go through this video lecture, and we're going to meet next time. Thank you.